Any other announcements? Okay, that's perfect. Great. All right, hey everyone, welcome to the lecture. Great. So before I hop in, we're going to do things a little bit differently today, and I apologize. I was a little bit late getting things set up. Looks like we've got 48 people in the class right now. That's great. Okay, great. Well, I'm just getting a few last things set up here. I'm almost ready to go. While I do that, so I know you guys went over the programming challenge. Thank you for doing that. Arvind and Rohan, any other announcements before we get into our lecture?
Nothing from my side, Professor. Like we
All right.
got the stage 2 project documents and the Jupyter notebooks. We are yet to go through it. That's it.
Excellent. Great. Perfect. Okay, great. Well, let me go ahead and hop to the schedule and let's have a look at where we're at. So let me do a quick screen share. And you all should have got a note on Canvas about some guided notes that will follow today. If you had a chance to print those, that's perfect. If not, that's okay. You can follow along with the PDF. But here is our schedule, and we've made it all the way into neural networks. We were just talking with our guest lecturer over email for Thursday. So this Thursday we have a guest lecture. Should be pretty interesting. Happily for you guys, there is no quiz or programming challenge due at the end of Module 3, but you will have one at the end of Module 4, so just make sure you're ready for that. So we've put these two modules together. And today we are on our third deep learning, or excuse me, our third neural network lecture. So today's lecture should be a lot of fun. And let's see, is there anything else? So Arvind has reviewed programming challenge number 2. Thank you, Arvind. That's awesome. You guys should be getting into your meetings now. So a number of your project groups should have already met with myself and your TA or just your TA. So those meetings should continue on. Hopefully this first project phase got you kind of going on your project and thinking about what you're going to focus on. It's pretty crazy. You know, there's, I think at this point, less than 2 hours, or excuse me, 2 months of the course left. So the clock is ticking. That's how it always goes in the fall. Things go really, really quickly. Okay, great. So that's just a quick catch up on where we are. You know, today we're going to dive deeper into neural networks. And you may be wondering, why is my camera facing down? Hopefully you can see this. Here's my hands. It's because I was talking to Arvind and Rohan, and last year in the course, actually the last 2 years, you know, we do these guided note things for this lecture. This lecture is the most math that you'll see all year. And it's a time that I really want to slow down and really spend some quality time on the math, because the math here really can, I think, empower you and give you a really good understanding of neural networks. And I think when we get into it, I think I'll zoom in here. I think this will work. Let's see, I'm going to be able to zoom in like this. And hopefully you're going to be able to actually read, and I'll switch this to my main screen in a second. But my plan here with this overhead camera view today is that we can kind of follow along these notes together. That's my idea. So we'll see how it works. Hopefully, technically, things will go pretty well. If not, we'll switch to a digital version. But you know, last year, basically, we had all the students print these out and actually write on them. And I don't know, people have different opinions on physical versus digital media. But when you're doing math like this, it can be nice to kind of lay everything out in front of you to kind of get your thoughts organized. And I think was it you, Rohan? Did you bring this up? I almost forgot about this. I'm really glad you brought it up. I think was it Rohan or Arvind that mentioned that you liked having the printed out physical kind of thing last year? Was that right?
Yes, Professor, it was me. Both of us had the same idea.
Yeah. Okay, great. Yeah, so I think there is some advantage to it. So those, you know, if you're following along, hopefully you've had a chance to print something out. If not, that's okay. You can follow along digitally. But before I get into that, this will be kind of the main thing for today. Before I get into that, and it's kind of funny to do a video lecture like this with the overhead, so you just see my hands, not my face. I don't know if that's cool or awkward. But anyway, let's hop into a notebook first. So first we're going to hop into and kind of finish our notebook from last time. And then we will get into those notes on back propagation. So let me go ahead and pick up. So it's 2:38, so we're doing pretty good on time here. So we've got enough time to get a nice lecture on neural networks in here. And yeah, let's go ahead and get started. Arvind and Rohan, anything before I start? Is that overhead view? I'll make it, well, when we get to that point in the lecture, I'll ask you guys to confirm you can read the text on my paper and stuff like that. Anything else, Arvind and Rohan, before I hop into lecture?
No, Professor.
Great. All right, cool. All right, guys, so you should be able to see my screen. So what I want to hop into now is I want to get a little deeper into where we left off last time. So we're talking about neural networks, and this series goes along with a YouTube series called Neural Networks Demystified. And the whole point of this module really is to get you into thinking about and kind of understanding the basic building blocks of neural networks. And as part of that, we're going to be, making a neural network from scratch in Python. And the thing here to keep in mind is that we're basically going to be building a toy neural network. When you get to the deep learning module and when you start working on your projects, you're going to be using a kind of different set of technologies. Let me just go ahead and hop to that real quick. So if I go to github.com/UNCCV, I bring this up because I know a lot of you are starting your projects right now. And as you start your projects, kind of doing modeling and coding and stuff like that, I don't want you to use the neural networks from this module. What I actually want you to do is to hop to the deep learning module and really check out this lecture. So on November 5th, we are going to talk about this really great library called FastAI. This library is a great starting point for deep learning. What we're doing in this module is we're really covering all of the inner workings of deep learning. How does neural networks, how do they really work? But when you go to do your project, I want you to be using the state-of-the-art technology in computer vision. And in my opinion, that really is FastAI. So really, this lecture is a great place to start. So as you're working on your project, I would recommend getting a little bit ahead if your project does involve deep learning. And I would not recommend, even though we're going to spend a lot of time kind of writing our own neural networks in this module, I would not recommend using these neural networks like the one that we code up here. Like, I would not use this neural network on your project, right? So this is really for educational purposes. And when we get, and you're going to use this on your programming challenge, but not on your course projects. So Hernan asked a great question. Yeah, thank you for clarifying, Hernan. So Hernan says, is this for the car project or for the course, right? So let me back up a little bit. So thank you for asking, Hernan. Let me slow down a little bit. So you have a programming challenge right now that is part of the autonomous driving module, which we're about to start next week. And your programming challenge, as I mentioned last time, is to teach a neural network to drive a car. For this, you will not be using that state-of-the-art tools. It'd be too easy. It would only take you like 20 minutes, maybe 10 minutes. You're going to be using your own neural network for this. So for this programming challenge, you are restricted to only use, you can use SciPy and you can use NumPy. So here, and that's on purpose to get you really comfortable with how these technologies work. But then on your course project, right? So on the semester-long course project that you're doing, there I do not want you to use just this simple neural network. That's where I want you to use FastAI. Hopefully that makes sense, Hernan. A great question. Hopefully that makes that more clear. Okay. So let's hop into our lecture here. And again, the purpose of today is to get down as deep as we can into how neural networks actually work. And then from here, it's going to be up with more and more complicated stuff. And until basically in about, let's see, 1 week, in 2 weeks, 2.5 weeks, we're going to be using the state-of-the-art technology. So right now, we've kind of dug down deep into the fundamentals to understand how the basics work. And next, we're going to kind of ramp up into the more state-of-the-art tools. Okay, this is as low as we go into the fundamentals. So to understand how neural networks work, what we've done basically is we put together a very simple neural network. And this is the same neural network that's in the video series, so I encourage you to watch that. I think that'll be helpful. The video series goes a little fast sometimes, so we really break it apart here to really kind of push your understanding. And just a reminder, we're working on this toy problem, which is that you recorded the number of hours you slept and the number of hours you studied before each test. You recorded your score on that test, and then you came back and you said, okay, let's try to predict how I will do on the next test given the hours of sleep and hours of study. So it's just a toy problem we're using to learn about neural networks. Okay. So we talked about our neural network architecture, we talked about synapses and neurons and activation functions, all this good stuff. We laid out our mathematics. What I really want to get to, though, is this. So we made some predictions. We talked about this. We talked about how our initial predictions weren't very good. And we talked about how our job when we're training a neural network really is to find the optimal set of weights. And our little neural network only had 9 weights, excuse me, it only had 9 weights. And originally, I kind of proposed this way of thinking about it. I said, okay, when we go train a neural network, our whole job is just to find the set of weights. It's to find the set of weights that minimizes our loss. that basically makes our estimate of y hat, as similar to y as possible. That's our job when we train a neural network. And remember that the idea here was to minimize this loss function, this y thing. Let me make this a little bit bigger. Our job is to minimize this loss function. And we talked about this idea, okay, you know, if we're just trying to kind of tune these weights, why can't we just try all the combinations of weights? So if you know the answer, throw it in the chat window. To train a neural network, why can't we just try all the different possible weight value combinations? What do you guys think? Why would that not be a good idea? So Videhi says impossibilities. I see continuous space, too much computation, lots of computing power, doesn't scale well. Absolutely. There's another name for this which I like, which is called the curse of dimensionality, which means basically it's going to grow exponentially, right? So it doesn't matter how powerful your computer is, pretty quickly you're going to run out of computing power, and this solution is intractable. So it really doesn't work at scale. So yeah, well said, everyone. Great. So we need a different approach. And there's this really beautiful idea. It's called gradient descent, and it's very connected to this idea of backpropagation, which we're really about to talk about in a lot of detail. And the idea of gradient descent is really this. It just says, okay, I'm not going to be able to test the value of the cost function at every point, but I can test it at some points. I can test my cost function. I can see what my error is at some value of W, of our weights. Remember that we have 9 weights, right? We have 9 of these. And the idea of gradient descent is like, okay, let's pick a combination of weights. And here I'm just showing you a kind of a one-dimensional projection. This is just one of our 9 weight values. Let's compute how we're doing at some location. And instead of searching the whole space, let's just try to figure out which way is downhill. What I mean by that is, you know, should I increase, or if I have an initial weight value, right? I have an initial value of W. Should I increase or decrease that W value to decrease my cost? Which way, you know, should I change W to decrease my cost function? That's the idea of gradient descent. And in gradient descent, we take these steps, they're just called steps. We take these steps downhill until we think we found the bottom, basically. So this is kind of demonstrating this concept in one-dimensional space. For this neural network, we're going to do it in 9-dimensional space. And then in a few weeks, when we do fast AI, we're going to do this in like 10 million dimensional space, which is kind of crazy. But this is the idea of gradient descent. I hope this idea makes sense. So instead of like basically trying every possible combination of weights, we're just going to start with one set of weights. We're actually going to choose them randomly, and then we're going to take that initial location and we're going to compute the gradient. We're going to say, okay, which way is downhill? Which direction will reduce my cost function? And then we're just going to iteratively take steps that way. That's the idea. Remember that about a week ago, you know, we introduced the perceptron algorithm, and the perceptron algorithm did not use gradient descent. Do you guys remember how did so the perceptron algorithm also took little steps, right? It took little baby steps, right? But it didn't use gradient descent. What did it do instead? If you remember the answer, throw it in the chat window. What did the perceptron algorithm do instead of this? How did it decide how to change the weights? So Monica's right, it was greedy. Can you be more specific though? What exactly? So Frank Rosenblatt invented this perceptron algorithm. What did he have us do? For every step, how did you change your weights? What was his advice? We add or subtract. What did we add or subtract, Videhi? What did we add or subtract? Yeah, the data, right? Abhijit, good. We added or subtracted the actual data, which is kind of interesting. That's actually related to gradient descent, but this is a little bit different. So this is a little more sophisticated. And I'll just say one more thing really fast. So this idea of gradient descent, there's actually a few ways to do it. If you want to figure out which way is downhill, like which way is going to decrease your loss function, you could actually just kind of do more tests. So we'll see in a minute how to compute the loss for a specific value of the weights. You could, like let's say you had a current value of 1.1. You could just test the value at like 1.2, and you could test the value at like 1.0. You could just test those values. If you did that, that would be called numerical gradient descent, and it works okay. But what's actually way more powerful is actually to use calculus. So we're going to do a bunch of calculus today. Because as you may remember, a big part of calculus is computing the slope of a function. So this idea of a derivative in calculus, kind of the beginning of calculus, a derivative tells us the steepness of a curve. So we can use calculus actually to estimate the steepness of our curve here, and that will actually give us a much more computationally efficient and robust estimate of which way we should move our weights. So that's the idea with gradient descent. And we're going to do it in high dimensional space. But one little question for you, and I might have just flashed the answer maybe. When will this not work, right? And I see one question coming in here. So Supreet says, is there a way to know we've hit the lowest close to lowest? Or is it just an assumption? Yeah, that's a great question, Supreet. So we're about to get into that in more detail. If I go back to here, right? When will this fail? Can someone tell me exactly, when is there going to be a problem? When will gradient descent? Yeah, when we hit a plateau, or even worse, yeah, basically a local minima, yeah. So our aparajitha, hopefully I got that right. You have it perfect, yeah. So this, oh, that's right, AJ, thank you. All right. So this can happen, right? We can hit a local minimum, right? So early on in neural network research, people thought this would kind of doom the field, like, hey, this is pretty damning. Like, what are we going to do about this? We're not going to be able to find the best solution because we might get stuck. It turns out in practice, this actually doesn't matter that much, which I know sounds crazy. But in practice, we can kind of ignore this idea, and usually, like, the thing about deep learning, so deep learning is very, very empirical. There's not going to be any guarantees. We can never really guarantee we found the best answer, but we can basically show empirically that we found a good answer. But no one actually knows if you found the global optimum. We can't prove it. So it's really interesting. It's an area of neural network research. Maybe in our lifetime someone will figure it out, but we really don't know today if we are able to find global solutions. Okay. So let's get into the meat of today's lecture, and these are the equations that we kind of set up that describe the mathematics of forward propagation, of moving our data all the way through our network and computing a loss function. And to actually do gradient descent, we have to compute two calculus equations. We have to compute the rate of change. And real quick, so when you first learned calculus, you might have learned like dJdW with like a regular case D. Here I'm using this kind of partial, this script D. So this means something a little bit different than just a regular D in calculus. Does anyone know, what does this curvy D mean? Why am I using a curvy D here? Yeah, it's a partial derivative, that's right, because we're doing, this is multivariate calculus. So if it's been a while since you've taken multivariate calculus, or if you've never taken it, that's okay. Just hang in there. There will be a little bit on the quiz for multivariate calculus, but it won't be too crazy. Hang in there with me. But yeah, so we are computing the rate of change of one variable with respect to multiple other variables, because these are matrices, so we're using partial derivatives. Okay, so hang in there with me. So we're about to get into that. So hopefully you've had a chance to print. Actually, I'm going to stop my screen share now. Hopefully you've had a chance to print these notes. And give me 1 second here to close this door so I have better lighting. And if you haven't had a chance to print the notes, they are in the repo, so you should be able to just go look at the PDF there. But what I want to get into today is, I'll zoom in a second so you guys can really see well. I want to start working through this math. How do we actually compute those gradients so we can optimize our neural network? And if you have printed this thing, what I'd love you to do, this is what I do when I'm really stuck on hard, complex problems, right? So for me, I really benefit from having like a bunch of physical stuff in front of me, right? Laptops are great, but for me, and this is different for everyone, I encourage you to find what works for you, but I'll tell you what works for me, is to have things like organized and spread out in front of me so I can really see everything. So what I love to do actually is to take something like this and like really spread it out, and I'll zoom in a second, like I said. But what I'd recommend you do, if you can, if you have the space on your desk, I know we're working from home and things are weird, but if you can do this, I really encourage you to find space for at least a few of these things at once, and maybe even look at it all at first. But really the big thing that I want you to have is kind of some scratch paper. And do I have this order right? Oh yeah, there we go. So there's 5 pages to this thing. Wow, this is more organized in my head. Okay, so there's 5 pages to this thing. What I'd really like you to have, if possible, so this first page, kind of the intro page, let's see if I can get autofocus to work. this first title page, it's not really focusing. That's okay. We want to have that out. We'll start on this first page. I'm going to put the other 3 pages away for a second, but you might want some scratch paper. So I'm going to grab some scratch paper. So I have these 3 pieces of paper, and let's really get into it here. Okay, so now I'm going to try to zoom in, and hopefully you'll be able to actually read what I'm writing. So this is the important test. So I'm zooming way in here, and here's kind of the first page of our stuff. All right. Is that legible? So throw it in the chat window. Can you actually read this? Do I need to zoom more? It's legible. Monica can read it. Okay, that's awesome. Great. And you should have the same PDF in front of you. All right, cool. So referring back to this sheet is going to be like really helpful. So this is going to have all our forward equations. It's a little hard to see in the image, but you'll see it on the PDF. Here's the neural network, a picture of the neural network. Here's our data. You've got it all here. Here are all our key variables. So I've got all our key variables laid out here. So you've got them all. You can refer back to them easily. And we're going to fight through here. And our goal, really, our whole goal, and my printer is a little messed up. It kind of chopped off the top. But our goal is to compute these things, right? We're going to try to find dJDW1 and dJDW2. And conceptually, the whole point of this is these things are going to tell us, they're going to tell us which way is downhill so we can optimize our neural network, so our neural network can learn. Computing this is like key to letting our neural network actually learn. Okay, that says which way is downhill. Maybe I'll zoom just a smidge more if I can. Do I have more zoom? That's all I got. Okay, that's my max zoom. Okay. So let's get started here. The first thing I'm asking you is to think about dimension. So let's see here. Please click on the view button in the top right corner. Okay.
It's for the students, Professor.
Oh, thank you, Arvind. Yep, great. Okay, cool. Thank you so much. Yeah, and what will that do, Arvind? That will make my video the largest screen. Is that what that'll do?
It looks good, Professor.
Okay, great. Just let me know if there's any issues. Okay, thank you, Arvind.
Sure.
All right, we're trying a little bit of a different technology solution today, and I didn't warn Arvind and Rohan. Sorry, guys. I just sprung this on them. All right. So let's get into it. So the dimension of dJDW1, and this is a little 1 right here. The dimension of dJDW1. That's our first thing. Okay. Now I'm going to grab my scratch paper real quick here because I kind of want to write down a little bit of thinking about these equations. So I'm going to grab my other sheet. So here's my first sheet. And if we look at what I really want to look at is that first equation. I want to get that first equation really, really clear. So this is the first equation. It's Z2 is equal to X times W1. So that's the very first equation. And in our image, or in our neural network, that represents going from our data, our inputs, through to this first layer. It basically represents the math of the beginning of going into our first layer. Okay, so here's that equation. Z2 equals X times W1. And let's get into it in a little more detail. So what does X represent? So throw it in the chat window. What is X again? What does that represent in our equation? Data, right? Perfect, good. And what is the dimension of X? What is the dimension of our data in this case? Now, this is a matrix, right? So it should have 2 dimensions. What by what? Remember that how many examples do we have? So look at that first page of notes, right? How many examples do we have? We have 3 examples, right, in our training set. Look at that. So open up your PDF or get out your paper and look right here at this table, right? So Hernan, you're close. That's the number of numbers in X. But I want to know, yeah, so Akshay is getting really close. I think Bonaventure has it. I think Bonaventure's got it. So look at my table carefully, right? So I'm giving you a hint. So if you look at my table on that first page, this is what I'm talking about having everything out at once. So if you look here at my table, right, I'm saying the dimension of X is the number of examples by the input layer size. That's the dimension of X, number of examples by input layer size. So how many examples do we have? We have 3, just like Preetha said. So we have 3 examples. And the input layer size is 2. Why is the input layer size 2 again? What caused our input layer size to be 2? Two features, yeah, exactly. We're measuring hours sleep and hours of study. Yep, perfect. So this is like a 3 by 2. Okay, cool. All right, Good deal. And I might fill that in a second, but that's okay. And now W. Let's go to W, right? So first of all, what does W represent? What does W represent in our neural network? It's our weights, good. And weights are learned, right? This is what actually does the learning, our weights change. And how many, let me go back to our picture here for a second. Hopefully you can see this picture, right? In our first layer here, right? How many weights are there total? How many weights are there total? There's 6 lines, that's right, good, because you have every input is connected to 3 neurons, right? So we have 6. And what is the dimension then? What is the dimension of W? What is the dimension of this guy? Of W1, excuse me. So there's 6 numbers, sure, but yeah, 2 by 3, yep, perfect, great. Yep, so it's a 2 by 3. Jeet's got it, Mir's got it, good, awesome, great job. A couple other folks have it, way to go. So it's gonna be a 2 by 3, like this. I'm just kind of drawing the shape that it'll take, 2 by 3. And I'm gonna go ahead and start using a little bit of a special notation. I'm gonna go ahead and start filling in these weight values. It's gonna take me just a second, but follow along if you're writing this down. So I'm going to fill in, basically I'm going to put in a placeholder for every single weight, all 6 values. So we've got, I'm going to call this W11 because it's the first row, first column. And it's our first weight value, like that. Hopefully that's coming through, so it's W1. And we've got W, this is the first row, second column. W2, like that. We've got W13, third. Got W21, 1, W22, 1, and W23 of 1. Okay, I might have to write a little bit bigger on the next one. I'm looking at my own phone, and it's a little hard to read. Are you guys able to read that? If not, I can move my camera. This is a little bit of an experiment today. So you can read it. Okay. All right. I'll write a little bigger next time too. It's okay. All right. I'll write a little bigger for the next one. So this is our weight matrix. There's 6 of them. Here they are. We're going to multiply our inputs. And let me go ahead and fill in some inputs just for fun. So we actually end up normalizing our input data. But I'm just going to go ahead and bring in the non-normalized data just for a second so we can kind of really think about it. So the first data, right, it's 3 and it's 5. And this represents 3 hours of sleeping and 5 hours of studying, right? Okay. And this gets multiplied by this matrix. And eventually what this formula is telling us is we're going to have some output, Z, which is the activation, which is kind of the output of that first operation in our neural network. Okay. And thinking back to your calculus for a second, what is the dimension of Z going to be? Actually thinking back to your linear algebra. What is the dimension of Z? Yeah, it's a 3 by 3, right? Good. A lot of folks got that right. Way to go. Cool, cool, cool. Okay, so this is going to be a 3 by 3 matrix, this Z thing, 3 by 3, okay. Cool, and I might fill in the values later if I want to. But for now, I just have one question. Why is it a 3 by 3? If we had made some different decisions about either our data or our neural network architecture, Z would have been a different dimension. Why is Z a 3 by 3? What 2 decisions or what 2 things are making this a 3 by 3? Yeah, so Hernan says it depends on the features and weight. So yeah, Hernan, I think you got it right. I'd like you to expand or someone to expand a little bit. So Hernan, I think, has said this well. Let's improve it a little bit. So number of examples, hidden layer size. Totally, yep. So yeah, so the features is kind of, although that's a little bit different actually, yeah. So yes, so the number of examples, that's one of the 3s. It's this 3 actually, I believe. And then and Sai, you're correct too, but the point I'm trying to get at here is, remember like we chose to have 3 hidden neurons, right? We could have had 4, right? If we had had 4 of these, then Z would have a different dimension, right? Z would actually be, it would actually be a 3 by 4. So I'm just pointing out that the shape of these matrices depends on the number of input examples, and it also depends on the number of hidden units. Okay, so finally we can kind of get to our, and yeah, Ravina, that's totally correct. Yep, that's the matrix multiplication works. What I'm trying to get at a little bit more to is the concepts here, right? What about our neural network is making our sizes be these shapes? Okay, so here we are, back to number 1. So we talked about the dimension of W. So remember that W1 is this weight matrix here, right? And I'm asking you, what about dj dw1? I'm asking about, I'll write it really big right here. I'm asking about dj dw1, right? That's what I'm really asking about. And first I'm asking for the dimension, right? Before I ask for the dimension though, how many, well actually let me back up even further. Is dj dw1, is that going to be a scalar or a matrix? So any guesses, scalar or matrix? Throw it in the chat window. What do you think? So Sai says scalar, Hernan says scalar. So good guesses. That is incorrect. So if it's not a scalar, it must be a matrix. Let's think about why it has to be a matrix. So I tricked a couple of you guys, and that's fine. I'm glad that you're participating. Please, it's always better to say something than to say, yeah, so I appreciate your participation. So that's wrong, and that's fine. So let's get into it. So this is, why does this need to be a matrix? So it seems like it should be a scalar, and I think I understand why you might think this is a scalar. It's an easy thing to think. Because J, so J represents, so let me ask you real quick, what does J represent again? What is J? It's the cost. And is J a scalar or a matrix? Scalar, yep, absolutely. So J is a scalar, right? Now, dJdW, it has to be a matrix. It has to be a matrix. Let's talk about why. So when we do gradient descent, when we actually do gradient descent, we have to know how to update all of our weights, right? And how many weights do we have? We actually have 9 total. 6 of them are in this W1 matrix here, right? 6 of the weights are here, right? So this has to tell us how to update every one of these weights. When we compute the gradient, this is going to say, oh, okay, increase W11 a little bit, decrease W12 a little bit, because it's like we're in high dimensional space, right? And the gradient is going to say which way is downhill in all 9 dimensions. So that's the idea. So with that in mind, then, what do you guys think about number 1? What should the dimension be of dJdW1? What do you think? If you think you have the answer, throw it in the chat window. Yeah, so Jagadish has it right. Good. It's a 2 by 3. It's actually just like our weight matrix because it really does the same thing. So the dimension of dJW1 is it's 2 by 3. So that's our first answer. So it's just like our weight matrix. So we need just as many gradients as we need weights. Okay, cool. Let's keep going. So dJdW2, the second thing here. Okay, let's think about this for a second. So let's go ahead and hop to let's keep moving actually. So what I want to kind of pick up here in this sheet is our thread of our equation. So this is equation number 1. We just kind of thought through the matrix version of this equation, right? Let's pull in equation number 2. So equation number 2 is A2. I always get these backwards. A is activity. Okay. So A2 is equal to F of Z2, like this. Okay, cool. So there we go. Now, what was the dimension of Z2 again? Throw it in the chat window. What was the dimension of Z2? 3 by 3. Thank you, Pooja. Yep, perfect. All right, so this goes right here. Now, the next important question. What is the dimension of A2, right? So this, let's talk about F for a second, right? So what is F again? What is that doing? What is F? It's our activation function, good. And it's a sigmoid function, great, fantastic. I didn't put it on the sheet, I probably should have. Well, maybe did I put it on the sheet? No, it didn't make it on the sheet, that's okay though. So it's in the Jupyter notebook. It's the activation function. And I'll go ahead and write it right here on the paper just so we have it. So we've got a definition. So F, we're using the sigmoid activation function here, which is 1 over 1 plus e to the minus z. That's the definition of F of z. Squeeze that in here. F of z is equal to 1 over 1 plus e to the minus z. But I really want to emphasize something here. I want to emphasize that this function is I'm going to call it an element-wise function. It's element-wise. So what does that mean? What do I mean that it's element-wise? If you know the answer, throw it in the chat window. What does that mean that this is an element-wise operation or an element-wise function? What do you think? What does that mean element-wise? Performed on every element. Yep, it applies. Yeah, it applies to every element in a matrix, and importantly, it applies to just like one at a time. It's kind of what I would say. So like one at a time. So there's no connection between the elements, is what I would say for each element. Yep. So if the input to f of z is a 3 by 3, what should the output size be? What should the size of A2 be? 3 by 3, right? Because it just applies individually to each element, kind of like each one is a scalar separately. So this is going to be a 3 by 3 here, A2, and we'll get into A2 in more detail, but this is going to be a 3 by 3. Okay, my camera will focus. Yep, kind of, sort of. Yeah, it's pretty focused. All right, great. Okay, so let's keep moving here. So this is equation. We just talked about equation 2, because what I want to get at is question 2, of course. Let's go ahead and hop into equation 3. So equation 3 says Z3 is equal to A2, which we just talked about, times W2, times W2. Okay, so there's our third equation, equation number 3 of our neural network. And this equation is really all about this part right here of our neural network. So going from here to here, it's moving us from our second to our third layer. Okay, and let's keep moving here. So we know that A2 is going to be a 3 by 3. And actually, this is going to be very important in a minute, so well, in a little while. So I'm going to go ahead and actually kind of write this out in a little bit more detail. So I know that A2 is a 3 by 3, and I'm going to fill this in more later as I keep going. But we're going to have like an A11. The notation quickly is kind of tiring to write because you've got a lot of variables floating around. And a big reason that I'm having you go so deep into the math of neural networks is I promise, kind of like if you spend some time on it, I hope that you come to realize that it's really not too bad. So if you've made it through high school calculus and you've made it through high school, and maybe a little bit of college linear algebra and enough college calculus, then it's really not bad. It's not too crazy. Now, if this still doesn't make sense, that's okay. You can still be a very successful deep learning practitioner. But the reason we're going so deep is because when you get to the bottom, it's really not that bad, I promise. And once you understand it, it can be really, really empowering. Okay, and it can help you, make better decisions as you work on neural networks and stuff. Okay, so here's A, right? And I'm about to ask you about W2 in a second. So A, we decided is a 3 by 3. Let me ask you first, before I ask you for the dimension of W2, how many numbers are in W2? What is the number of elements total? How many W? There's 3 of them, right? There's 3 weights in W2, perfect. Let's take a guess now. What is the dimension of the matrix W2 then? What do you think? What is its dimension? 3 by 1, yep, perfect. Good. So you could have gotten that off my table, or you may have just figured out that, hey, if it's got to get multiplied by a 3 by 3, the first dimension must be 3, and there's only 3 elements in it, so it must look like this. So I've got something like this, W21, W31, and this is W2. Okay, cool. All right, so that's that equation. What will the resulting output be then, right? So I've got a 3 by 3 and I've got a 3 by 1. So the output, thank you, Rohan, is going to be a 3 by 1. Yep, perfect. Okay. So Z3 is going to be a 3 by 1, kind of like this. Okay. So let's get back to our question now, and I'll finish walking through the math in a second, but I think we can answer this question now. So I'm asking for what is the dimension of, and I know that's a little blurry right now, but that says dj dw2, and you should have that PDF in front of you too. What is the dimension of dj dw2? So if you know the answer, throw it in the chat window, please. Yeah, it's a 3 by 1. Yep, perfect, Sumak. Yep, great. So it's just like W2. It's the same dimension as W2. So it's going to be a 3 by 1. Okay. Alrighty. So let's keep moving here. So when we get to number 3 here, what I'm asking you to start doing is to really kind of start from the end and work backwards with our forward propagation equations. So let me actually go a little bit further with kind of my walkthrough of the math, because then it's going to be easier to go backwards. So we have an equation for number 3. We kind of made it to Z3. So let's go ahead and write down equation number 4. So equation number 4 says, y hat, let me scooch this up a little bit so you can see it. It says y hat is equal to f, which is our activation function, our sigmoid activation function, f of z3, like this. Okay, and remember the dimension of z3. So z3 we decided is a 3 by 1. It's a 3 by 1. Okay. So what is the dimension of y hat then? What is the dimension of y hat? If z3 is a 3 by 1, what must y hat be? Yeah, again, it's a 3 by 1. Perfect. Okay, good. And that's because f is element-wise. It only applies to every element in this matrix separately, so it will never change its dimension. Okay. What does y hat represent in words? We talked about it a little bit last time. What is y hat? What is that? How would you describe that in words? It's the prediction. It's the estimate. Yeah, exactly, right? Perfect. And right now, how many data points have we plugged in to this forward propagation that we're doing? How many x values did we start with? How many samples? 3. And how many outputs does it look like we're going to get? How many outputs? 3, right? That should make sense, right? If you plugged in 3 things, you should get 3 things out, hopefully, right? If I had plugged in, if way back here, if my x had been like 4 things, right, I should get 4 things out with y hat. And if you do that math, you will. Okay, so that's y hat. It's our estimate of y. It's a 3 by 1. And now the very last thing, so equation 5, so we made it to equation 4, and we're about to kind of work backwards. So we made it to equation 4. So now equation 5, this is our loss function. So equation 5 says j, I'll try to make this nice and big. It says j is equal to the sum of 1/2 times y minus y hat, like that, squared. Okay, so this is equation 5. This is our cost function, because the lower we can make it, the better our neural network is. It describes the cost of getting the answer wrong. And let's talk about dimensionality again, real quick. So we just talked about y hat, right? So y hat is, we said, a 3 by 1 because we have 3 examples we've passed into our neural network. What is the dimension of y? So our data, right, our labels. What is the dimension of y in this case? So good guess, Abhijit. It's not a scalar. Good guess. So remember that y, it's this, because we have 3 examples, right? So yeah, so it's a 3 by 1, right? So Sai, Akshay, great job. Good, good, good. So this is a 3 by 1. Cool. All right. Cool. So it's a 3 by 1 as well. And that should make sense because we have to subtract these, right? So we're subtracting a vector from a vector, right? And it should make sense too that we want to subtract like the first example from the first estimate, right? So the first y hat we get out, that first value in the vector, that represents our prediction for the first data point. And we want to subtract the prediction or the ground truth value, because the more different these are, right, the bigger the cost function will be. And that'll be a larger function that we want to penalize, basically. So this is taking the difference between the prediction and the ground truth. That's the whole idea. Now this sigma, this summation, right, what will that do, right? So this will take our 3 by 1, and what will the output be? I asked you guys this a minute ago. What will the dimension of the output be, Jay, after we do the summation? Yeah, it's a scalar, right? So I'm just going to say it's just like a 1 by 1, but yeah, it's just like a scalar, right? Yep, totally. Okay, cool. So now remember that we are trying to compute, to kind of tie all this together for you, hopefully, right? We're trying to say, okay, what math do I need? You know, computationally, I want to minimize this. I want to make this as small as I possibly can, right, J? And I'm going to wiggle or change the values of W2, and I can change the values of W1, right? I can change both these values. I can change W1, I can change W2. And to figure out how to change those values, right, I need to compute the gradient to figure out which way is going to, what kind of changes in W are going to decrease J, which way is downhill. So I'm going to compute dj, dw2 first, and then we'll go back and compute dj, dw1 if we have time. Okay, so that is the whole idea, right? Can we connect these two things mathematically, right? Can I compute the rate of change of this with respect to that? That's what we're going to try to do next. Okay, and we're going to do it one step at a time. So let's get into it. That's what these notes are here to guide you through. So in number 3 here, I'm saying, okay, all I'm going to do to get started, so I want to compute dj to w2. I'm going to substitute in what I know j is. So if you look at your formula for j, you should have the sum of 1/2 times y minus y hat squared. So I've just substituted. Here I've just taken that formula and I've popped it in. And now if you remember from calculus, there's something called the sum rule. The sum rule says that the sum of the gradients is equal to the gradient of the sums, which means that I can take this sigma and I can actually move it outside. So that's pretty simple. Let me show you how it works here real quick. So all we do for this one is we take this big sigma, we move it to the outside like this, and then we put our equation on the inside. So 1/2 1/2 times y minus y hat squared over, and did I forget my, oh yeah, yeah, I kind of want to put my d right there. I'll put it right here for now. So I forgot my derivative sign right there. And on the bottom, I'm going to have d w2. So all I've really done, right, all I've really done is I've taken that, I've taken this equation and I've moved the sigma outside. And I can do that because of what's called the sum rule in calculus. Okay, so in number 4, here's what I'm saying to you. Number 4, I'm saying, okay, let's temporarily forget about the summation, because this summation, remember that this summation actually is summing across the examples. So, you know, if we have 3 examples, we're summing 3 things together. If we have 4 examples, we're summing 4 things together. And the same mathematics should really work if I have 1 example as well. So for the next 5 or 6 problems, we're only going to consider 1 example at a time. We'll just say, let's assume that we have num examples equals 1. And that'll make our math a little bit easier. Then we'll add back in the rest of the examples. Okay, cool. So let's keep moving here. And let's start thinking about how to actually take this derivative. So if we only have 1 example, then basically the summation goes away for now. We'll add it back in later, but this is going to go away. And what I want to think about now is actually doing this derivative. So hopefully, you know, hopefully this is ringing some bells back to calculus and you have some memories. Like, let me just give you a very simple one. So back when you took calculus, if you haven't, that's okay. You probably learned something like this. Maybe you learned like how to take derivatives of functions like y is equal to, let me just give you one, 2x cubed plus 3x squared or something, right? So this is a polynomial equation, kind of some of the easier things to deal with in calculus. So yeah, how do we take that derivative, right? So if I said, hey, please tell me what y prime is, right? Please give me the derivative, the rate of change of y with respect to x. So if you know the answer, throw it in the chat window just to see how you guys are feeling about this. What is the derivative, right? So 2x cubed plus 3x squared, what is y prime? So a lot of people are answering right away. That's a good sign. So I've got a 6x squared plus 6x. Yeah, I kind of didn't mean to make it come out that way, but yeah. So we've got 6x squared, right, plus 6x. That's the right answer. And for those of you that got it right, what did you do? How did you know that it was the answer? What rule did you apply? Yeah, so it's called the power rule. Great, good deal. So this thing is called the power rule. And what we do is we take our power, we bring it down to the front, we multiply it, and then we subtract 1, right? So 3 times 2 is 6, subtract 1, you get 2. So that's the idea. And there it is, stated very beautifully by Sai. Nice job. Cool, with ends and everything. Great, Ravina and Sai looks good. Cool. So that's the power rule. So that's what we're going to do here. So we're going to apply the power rule. So nothing too crazy. So let's do it. So you're actually about to see why we have that 1/2 in our equation. It's to make our life easier. So this 2, right? This is going to get brought down in front, right? It's going to get brought down in front. So 2 times 1/2. Last time I checked is 1. So let me go ahead and start writing the answer down here. So this will kind of cancel out. So we're going to have a y minus y hat. We're still going to have that, okay? The 2 and the 1/2 are going to cancel. The leftover power is just going to be 1, so I'm going to leave that alone for now. Now, we aren't quite done yet. There's something that makes this a little bit more complicated. There's actually 2 things, really. So let me just ask the class real quick. Ideas why we aren't done yet. Why can't I just do the power rule? Why can't I just bring the 2 down, subtract the 1, I get a 1, you know, everything's good. Why am I not done? What am I missing? Yeah, so the ddx, sure, derivative, yeah, right. And what Tsai and what Hernan are kind of mentioning here, inner derivative, yeah. Does anyone remember the name of the rule that we use in calculus to deal with the inside and outside derivatives? What is that rule called? Yeah, the chain rule, right? Yeah, thank you, Adam. Cool. Yep, so it's called the chain rule. Great. And maybe you learned it by a different name. That's fine if you did too. But what we're dealing with here is the insides and the outsides, right? So we're not done because we have to think about now the derivative of the inside function. So we've kind of done the power rule for the outside, but now we have the inside to deal with. Okay, so first of all, I want to deal with this negative, right? So the derivative of having this minus here basically means we have to deal with the derivative of minus times some variable. So what really happens here is this just ends up being a minus, which I'm going to put right here. That's the minus part. But the other thing to consider is that each of these, the y and the y hat, these could have derivatives with respect to W2, right? With respect to W2. Now, one of these things actually doesn't. So one of these two variables, the derivative with respect to W2 is actually 0. And I can tell you that right away, but we'll ask you why in a second. The other one we have to kind of deal with. But let me just ask the class now. So one of these two variables, its derivative with respect to W2 is just 0, just categorically. Who knows which one and why? Why do one of these terms we don't have to worry about? Which one do we not need to worry about and why? So I see some y hats, I see some y's. Yeah, so I think it just flew by. So yeah, Maheshwara, sorry for the pronunciation. Yeah, you have the best answer. Your spelling is not great, but your answer is perfect. So you said yeah. So and AJ, yes, absolutely. So we're not going to worry about y because it's a constant. So y is our data, right? So y is not going to change. If you change W2, it's not going to change our data, right? So y is a constant. It's not going to change. So its derivative with respect to w is 0 because doesn't matter what w is, our input data is always the same. Now y hat is a different story. So y hat, as you guys know from all this work I just did, hopefully I convinced you here that if I change some w values or some w2 values, then y hat, it's definitely going to change, right? It should change, hopefully, because we want to make our predictions better by changing our weights, right? So we have to think about this, and it's going to take some more work. But for now, all we're going to do is this. So we're going to follow the chain rule. We're going to do the derivative of the outside times the derivative of the inside. We dealt with the negative sign. Now we're just going to do this. We're going to say times dy hat dw2. So basically we've said, okay, we have to deal with the derivative of y hat with respect to w2. We're going to express it like this. Here's the equation. And now we have some more math to do. So we're kind of going to have to go deeper. But this is the beginning. This is our first step. So we've begun to compute djw2. We could go, if we were writing code for this, you could go ahead and plug, you could write this in Python, you could write this in Python. This you can't yet, right? This is going to take some more math until we can express this in terms of some vectors that we already know. Okay. Although actually with PyTorch you could do this, but we're not doing PyTorch yet. Okay. So let's keep moving. So now I'm asking you to use the chain rule again, and I want you to basically break this apart. And this step is actually pretty straightforward and simple. I'll go over this quickly because I don't think this will present too much of a challenge for you guys. Do please come back and review if it doesn't make sense and look at, you could watch the video again. But all we're going to do here is we're going to take this term and we're going to break it into two other derivatives. And let me actually just explain a little bit of the motivation. So if you think about the connection between y hat, our estimate of y, and then w, there's kind of two things that happen in the middle. So first, w gets multiplied by a, and we get z, and then z gets passed through f, and that becomes y. So there's two steps. There's two steps that happen. I would like us to handle the calculus for those two steps separately. So what we're going to do here is we're going to use the chain rule again to break that apart. So it's going to look something like this. So it's going to be times dy hat dz3. This is kind of the intermediate variable between those two. And I think it's helpful too to look back at your first sheet and look at these equations. You'll see that z3 is the variable that links together those two variables that we're worried about. So we're going to express this as dy hat dz3 times dz3 over dw2. So hopefully this makes sense. This might ring a bell. Your calculus teacher might have shown you something like, oh, hey, these two terms kind of cancel. Now, these are not fractions in the sense of like, the fractions you would have learned in elementary school. But the same kind of thinking applies that we can use the chain rule to break this apart into two separate partial derivatives that are equivalent to just this one partial derivative, because these terms kind of like cancel. Okay. So that's all we're looking for number 5. Let's go ahead and hop into number 6. So one of these terms, I believe it's this one. So if we think about this term, right, if we wanted to start thinking about this term, right, we can actually think about it in the context of just one equation. So really this equation, number 4, this has y hat equals some function of z3. And we're interested in computing the derivative of y hat with respect to z3. So really it's equivalent to the derivative of this function, the derivative of f. So I'll keep moving here. Hopefully that makes sense. If not, check out the video or walk through the notes later, or ask the TAs. So let's keep moving here. So I want to compute the derivative of our activation function. So there's our activation function. So I'll write this nice and big. So we've got 1 over 1 plus e to the minus z. Okay, cool. All right. And actually, I kind of have a question for the class. So we have a cool class that's, we have a good international student representation in the class. So, I went to secondary school in the United States. And for me, I took calculus as a high school senior. So I was like 17 years old when I took calculus. I'm curious kind of what, depending on where you come from, your school is going to be a little bit different. Just for fun, throw in if you have taken a calculus class, or if you haven't, just say I haven't. Throw in the chat window what age you were when you took calculus. Like what age did you first learn calculus? 11th grade for Monica. Okay, cool. Yeah. Sophomore. Wow. Okay. 16, 11, 16. Yeah. Okay, cool. 11. Wow, man, that's pretty cool. Yes, I was 17 years old. Okay, cool. Right. Interesting. Awesome. Everyone's ahead of me. That's great. Second college degree. Yep, that's cool. Yep, 32. That's awesome. Good, good, good. Cool. So we have a little bit of spread there. That's great. Awesome. And yeah, in the US especially, calculus is optional for most students. You don't have to take it, which is interesting as well. Okay, cool. And again, you don't have to be a calculus expert to do well in computer vision. Also, Dinesh is saying it's required in India. So everyone has to take calculus. That's pretty cool. Yeah. And again, you don't have to be a calculus expert, but if you know enough calculus, it can be really empowering because you'll really understand how these things work. Okay, great. So let's hop into it here. So here's our sigmoid function. Let's take a derivative. I'll just walk through my way of doing this. There's a bunch of ways to do this. I'll just walk through how I would do it. So I would actually kind of rewrite this as this. It's the negative first power. So I can use my power rule. I'm going to use the power rule to bring this in front. So first I'll transform it like that. So it's going to be minus 1 plus e to the minus z. I'm going to subtract 1, so I'm going to get minus 2 like that. And then times the derivative of the inside, which I believe is minus e to the minus z, I believe is the derivative of the inside. So I'm going to get something like, e to the minus z over 1 plus e to the minus z squared. And this can be simplified actually a bunch, but I'm not going to worry about it too much right now. If this was a quiz, I'd be plenty happy with this answer. So there's my derivative. Hopefully that makes sense. If it doesn't, don't worry about it too much. You can ask the TAs. This could be something that we would ask you on a quiz, something like this, but it wouldn't be quite like this. We would make it more relevant to computer vision because this is kind of a generic calculus question. But so that's the derivative of our sigmoid function. We can program this in Python now, and we will. That'll be part of making this whole thing work. So that's page 1. Hopefully that all makes sense. Let's go ahead and pop to page 2. So we've done a bunch of stuff, and we're getting there. We're making progress. How much time do we have? Only 15 minutes. Gosh, this lecture takes a long time. Okay, all right. So here we are on page. It's page 3 actually. Okay, cool. So we're on page 3 now. Oh, and that's am I showing? Yeah, I'm showing you the answers. That's funny. Where's my blank page? Please bear with me for 1 second. I have my answer page to make sure I don't tell you guys the totally wrong stuff. All right, cool. Here we go. Okay, so we now have an equation that looks something like this. Notice that I've substituted in f prime of z3, which we just computed, so that's been substituted in. And now we're going to simplify our equations a little bit, and if you look at some of the literature and some of the textbooks, they will use this thing called a back-propagating error, and that's just defined as the difference of our two outputs times the sigmoid activation function. So really we're just saying, hey, let's call this whole thing sigma. Okay, cool. So let's keep going now. So number 7, this is our next big important question, I would say. I'm asking you about the dimension of sigma 3, about our back propagating error, which is defined as y minus y hat times f prime of z3. And recall that we've simplified our problem for now, and we've said, okay, let's assume that we only have one input, right? We only have one piece of data we're going to process at a time for now. Later, we're going to expand it. So if you know the answer, throw it in the chat window. If we only have one example, right, what should the dimension of sigma 3 be? What should the dimension of that matrix be? What do you think? And if you're confused where to start, look here, right? Look at this equation. This should give you a hint, because if you only have one example, right, what is the dimension of y? What is the dimension of y hat? Yeah, so Sumuk, you nailed it. Good job. Yeah, so this is a 1 by 1. 1 by 1 is the answer. So let's talk about y. So the reason it's a 1 by 1, if I do this again, I have to fix my camera focus to make sure it's not going in and out of focus like that. It tries to focus on my hand, and the screen is out of focus, or the page is out of focus. Okay, that's a computer vision problem, right? Okay, here, right, if we only have one example, right, then the dimension of y is going to be 1 by 1. Y hat is also 1 by 1. We're only predicting one thing. And then remember that this is just a scalar function, right? It's just a scalar. Actually, no, did I make a mistake? Oh, this is why I have my answers in front of me. It might actually need to be a 3 by 1. Let me make sure I'm not crazy. Hold on. No, it's 1 by 1. Okay, good. Sorry if I scared you. Yeah, so this is going to be a 1 by 1. Okay. Because by the time we get to here, we've already summed back together. What I was kind of thinking is that, hey, you know, out of our neural network, we've got 3 connections coming in. So maybe I have to sum across these. But by the time you get here, you've already summed across these when you do your matrix multiplication in equation 3. So you basically are down to a 1 by 1. So the dimension of delta 3, if you only have one example, is 1 by 1. Okay, let's keep moving here. So now what I'm asking you is, I'm saying, okay, we're almost there, but we got to go work on this thing, right? I'm pretty sure everything I've given you so far, I believe you could plug in and you could write in Python. I think everything I've shown you in this equation, you could make happen in Python. The thing that you can't write in Python yet is this, right? We got to figure out an expression for this in terms of the matrices we already know, or the matrices that we can write up in Python using matrix multiplication and things like that. Okay, so to get started working on this, I want us to write out the full matrix equation for equation 3 using the number of examples equals 1, input layer size is 2, and hidden layer size is 3, and output layer size is 1. These are all equivalent to how we started, except I've dropped this down to 1, as we talked about earlier, to make life a little bit easier. So we already have an equation, actually, that we've written out for number 3. It's right here. It's this one. Here's equation 3. But now, remember that this equation 3 was assuming that we had 3 input examples, right? 3 input examples. But now we only have 1, right? So how will this equation change if we only have one input example, or we only have one input example? So think about it for a second. Take a second. First of all, if we only have one input example, right, our weights really shouldn't change. We should still have 3 weights, right? So that's going to be exactly the same. So I'm going to go ahead and write our weights kind of off to the side here. So we have W11, W21, W31, and these are W2s, our second weight matrices. Okay, cool. And let me ask you, so here is our activation matrix for when we have 3 input examples, right? This is a 3 by 3. What will the dimension be if we only have one piece of data to process, only one input example? What will this dimension change to? Yeah, so thank you, Abhijit. It is a 1 by 3, right? Perfect. So what I can do here is I can write this. I can write A11, A12, A13, and this is 2, 2, 2, like that. Okay. Cool. So this is going to be our new equation. We've written this out, and actually let me ask you real quick, well, the output dimension here is just going to be a scalar, so it's just going to be a 1 by 1, which is going to be z3. Okay. All right, so that's going to be our new equation there. And now we're going to use just a little bit more calculus, so bear with me here. So we're almost there, so we're going to compute dz dw3, so which is kind of our last missing piece to get this whole equation for dj dw2. So we're almost there. And now, what I want you to do is a little bit of calculus with me. Let me actually write one thing out for you real quick. I'm going to rewrite this equation. I'm going to rewrite this kind of as a non-matrix equation. So I'm going to write this. You could also write this, right? You could write this as A11 times W11 plus A12 times W21 plus A13 times W31, like that. And I need some 2's up here like that. And I need some 2's up there like that. Okay. So now, bear with me for a second. I'm trying to compute the rate of change of z, this thing over here, the output, with respect to each of those w's independently. W11, W21, W31, right? That's what I'm trying to do. Okay. So to do that, right, let's think about how this is going to change, this output, as a function of these inputs. And this is dz dw, right? And you can kind of think about this. What I really encourage you to do is, way back at the beginning of calculus, you probably learned something like, how to do equations like this. So let's say you have y is equal to a times x, for example, where a is a constant and x is a variable, right? What is y prime in this case? What is y prime for this very simple example over here? It's just a, exactly right. It's the slope. It's like the slope of the line. Yep, perfect. So this is actually really the same thing. It's really the same exact idea. So here, w is our variable, because we're thinking about, okay, how does our output change with respect to our input? These are our two variables. And a is like our constant. A is like our slope. It might seem weird that a is a constant, but in this case it is, because we're processing one layer at a time. And a is kind of a result of our data, and our data is fixed. So a is like a constant. So what happens then is our answer is just going to be, like, this term is just A11. It's A11 of 2, like this. Because the slope of this line, or you can think about it like this, it's really just like solving a very simple equation, or just like this, right? But it's in 3 dimensions, but happily the 3 dimensions are independent, because there's just a W11 term here, and it's added together with a W2, and they're not like multiplied. So we can totally separate out our dimensions. So our dzdw2 thing, it's just this. It's just the a's. So that is dzdw2. Hopefully that makes sense. At the end of the day, it's really just as simple as it comes down to this. It's just in higher dimensions. We're just separating it apart. So this is dzdw2. And now we're really almost there. So we're getting close to what's going to be something we could write in Python. So hang in there. So this dz3dw2, right? We just decided that we can write it like this. And now I want to write it in terms of just a single vector, right? Remember that this is a2. A2 is this thing, right? This whole thing is the vector a2. And then this is actually dzdw3. It's similar to a2, but it's a little different. What is the linear algebra term that turns this into this? How do you turn a row vector like that? Yeah, transpose. Yep, perfect. It's a transpose. So really all we have to do here, it's this. So it's A2. I'm going to put it in parentheses to make it really clear. The answer to this is just this. And that's something we can do in Python, right? So it's just A2 transpose. So that's it. So dzdw2 is just A2 transpose. Okay. This lecture every year, I don't know if you guys remember Rohan and Arvind, but this lecture took longer than I thought last year too. So we'll figure out what to do for the rest. This next question, guys, so we're just about out of time, but this next question, number 11, this is like super similar to what you are going to see possibly on a quiz. I'm kind of tempted, so it's class is over, so we'll let everyone go for sure. Since we are recording Arvind and Rohan, we could actually go a little bit over so I can get through this example, and then students can come back and watch this clip a little bit later to get ready for their lecture or for their quiz. We'll just make sure we'll get this video posted quickly to make sure they can get to it. Does that make sense, Arvin and Rohan? So we can formally end class now, but we'll keep the recording going, and then I can do this example. So if you aren't able to stay on, students, you can hop on YouTube and watch this remainder as you get ready for your quiz, because you'll have a similar question to this on your quiz. Does that make sense, Arvin and Rohan?
Yes, Professor.
Wonderful. And do we have a group meeting at 4 today, or is what's our schedule like for our meetings today?
It's at 4 today.
Okay, so we only have 15 minutes anyway. Okay, so we'll go like 5 or 10 minutes longer. And yeah, so students, if you're able to stick around and watch it the first time, perfect. If you have to bail, that's totally fine. I get it, it's 3:45. Thank you for coming today. And I'm gonna go ahead and spend 5 to 10 more minutes. I'm gonna walk through this, and then if you have to leave now, that's totally fine. We will work on getting you that video quickly so you can come back and watch it if you need to. Okay. And the reason I want to do this is, like I said, you're going to have a similar example. And this is about as far as I want to go. So really, there are some more notes. And if you want to walk through those, please feel free. But really, getting through this problem, like this is kind of the level of understanding that I'm looking for on the quiz. So that's why I want to just get through one more thing, and then you'll be in pretty good shape. Because you do have a guest lecture next time, and it'll be a great guest lecture. So we gotta wrap this portion up and keep moving. Okay. So this problem, right? I'm asking you to actually do this with some real numbers, right? So let's get into it. How does this work? Let's do it with some real numbers. So I'm giving you a real x value. Well, you know what I think I've forgotten to give you? No, actually, I guess I haven't. No, I think I need to give you a y, I think. Do I give you a y here? This might be missing a y. We'll figure it out. Let's get into it and see what we need. So I'm giving you some very simple weight values. I'm giving you an x value, and I'm asking you to find djw2. So let's get into it here. So let's start with our very first equation. So our very first equation is Z2 is equal to X times W1. So here's our first equation. Okay, so let's start plugging some good stuff in here. So we have X, we have W1. So this is going to be 0.3, 1.0. Let's see, and I've got 1, 1, 1. Wait, is that going to work? Am I already in trouble? Oh, I used the wrong W. That's funny. All right, so W1 is like this. I was like, man, I already broke the equation. That's not a good sign. All right, cool. So there's X times W1, and let's do it. So 0.3 times 1 plus 1 times 1. And actually, before I do the math, let's get into our dimensions. So this is a 1 by 3. This is a, sorry, 1 by 2. This is a 2 by 3. So these are going to cancel. So our output is going to be a 1 by 3. Hopefully that makes sense. And for each of these cases, it's just row times column. So I think the answer we're going to get is 1.3, I believe. We're going to get 1.3, 1.3, 1.3, I believe, for our 3 values. So that is Z2. That's Z2, our second layer activities. We're going to pass these through our activation function. So our next equation, so this is equation 1. Our next equation is A2 is equal to, get this out of the way. Okay, cool. So A2 is equal to F of Z2. Okay, and this part you'll need a calculator for. So all we're doing is we're passing in 1.3, comma 1.3, comma 1.3. Okay, cool. And let's do it. So we're passing in 1.3, 1.3. Remember that F is our activation function. So F is equal to 1 over 1 plus e to the minus z. So 1 over 1, I'll just compute it for one of these values, e to the minus 1.3. So if I grab my calculator here, we're going to do 1 divided by 1 plus e to the minus 1.3. Cool, and I get 0.79-ish, something like that. Okay, so I'm getting 0.79. So A2, and this is that element-wise operation, right? We just do the same thing to every element. So 0.79, comma 0.79, comma 0.79, right? That is what we get. Okay, so that's A2. Let's keep moving. Remember, we're trying to find, what are we trying to find here? I asked you to find dJDW2. So we're going to kind of do forward propagation, get to y hat, and then we're going to kind of compute dJDW2 using the equation we just figured out. So let's keep moving. So our next equation is going to be Z3 is equal to A2, which we just computed, times W2. And I gave you W2 in the problem. I said it's just 1, 1, 1. So let's do that. So this equals 0.79 comma 0.79 comma 0.79 times 1, 1, 1. Okay, so we just have a row times a column. So it's really going to be 0.79 times 3, which is going to be 2.36 is what I get. So I get Z3 is equal to 2.36. So that made us there. And then finally, we're going to do y hat is equal to f of Z3. Okay, so this is 1 over 1 plus e to the minus 2.36. So I'm going to plug that in now. I'm going to get back this equation, 2.36 when I plug in. And you could use Python or something if you wanted to or whatever. Thank you so much, Sai. Yep, so 0.91, correct. So we get 0.91. Thanks for following along. It makes me more confident that I'm doing it right. All right, cool. So that's y hat. That's our estimate of y. And yeah, what I actually didn't give you on this problem, so I'm glad we're doing this here. I forgot to tell you y. So let's pick a value of y. Just to stick with the same theme, let's say that y is equal to 1.0. So let's say that's our ground truth value that's going to be given to you in the problem. So y is 0.9 or y is 1.0. So that would be given to you. So we can go to equation 5 now. So we'll do j is equal to the sum of 1/2 times y minus y hat. So in this case, I said, hey, y is 1.0, y hat is 0.91. We're going to square this, okay? So the difference between these is 0.9, so we got a sum of 0.09, excuse me. 0.09 squared, is that 0.0081, I think, or is it 0.081? 0.0081, okay. And then I'll go ahead and do the 1/2 thing, times 0.5. So for my cost, I'm getting, and actually, you know, I didn't ask you to compute cost, so I've actually done a little more work than we have to. We don't actually have to compute cost, but this is the cost value you get, which is something I could definitely ask you on a quiz. So I get something like this for my cost. And what I did ask you for, though, and it's 3:51, so we're doing fine. We'll spend a few more minutes to get the final answer. What I did ask you for is dj dw2 right here. And we're going to use this equation that we determined up here, and we figured out that A2, that dzdw2, that missing term, we figured out it's just A2 transpose. So I'm going to actually put all that together into an equation, and I'll go ahead and give you a little tip that you shouldn't really need it, but I'll go ahead and share it with you just so you have it. So what I'm going to do is I'm going to steal this equation that we figured out earlier. So we've got dj dw2, which is, this is what we're trying to figure out, and that's what we've asked for, what I've asked for, is equal to minus y hat times f prime of z3. Okay, and then this we figured out is just dzdw2. In the one-dimensional case, for one example, it's just A2 transpose. And it turns out in the multi-dimensional case, this is kind of the rest of the guided notes, it turns out that it's still just A2 transpose, but you actually want to put that transpose in front of your equation. Let me just double check that real quick. So I don't think we'll make it through all of the guided notes, and that's okay, but I just want to make sure that I'm giving you the right equation. So if you do look at the guided notes later, if you want to go a little further, which you don't have to, it's not required, but if you do go a little further, I just want to make sure I give you the right equation. Let's see, yeah, right. So yeah, if you put this A2 transpose in front instead of having it at the end, then this will work in the multi-dimensional case, and I'll write it down really nicely. So you write it like this, so minus A2 transpose. And it doesn't actually matter in the one-dimensional case, which we're solving right now. In the one-dimensional case, you can put the A transpose at the end or at the beginning because everything's just a scalar. But if you're doing the case where you have more, why is that? Okay, I think I have this right. I'm going to double check after lecture. Z3. The hardest part of doing all this calculus is just keeping everything straight, because there's like 5 different things you have to kind of keep going. But when you really get down to it, as long as you're organized, like, it's really not that bad, which is, I think, one of the reasons I think it's worth spending time on. Okay, I'm going to double check that that's the right equation, but I believe this is the answer to number 15. So if later, if you're going to look at the higher dimensional case, it should be something like 15. It should be something like that. Okay, now back to finally answer this question, because this is a question, like I said, that I certainly could ask you on a quiz, and I want to make sure you're prepared for it, and I'm giving you everything you need. So let's get back to our quiz question. And where is my work? Oh, here it is. So here's my work so far. And we're trying to compute dJDW. And I just wanted to triple check that I'm giving you the right equation that's going to do everything you need. Okay, yeah, so y hat f of z3, and then this we decided was A2 transpose. Okay, cool. All right, so here's our equation. We're gonna do it. We're almost there. Hang in there with me. All right, so we made it to here. We've got this equation. Now we're gonna plug everything in we've computed to compute dj, dw2. Remember, we should get 3 numbers out because there are 3 w2s and we have to update each and every one of them. Okay, so minus A2 transpose. So we computed A2 earlier. For A2, we got this thing. We got 0.79, 0.79, 0.79. If we transpose it, we're just going to change it so it's a column vector. So 0.79, 0.79, 0.79, just like that. And then here we've got y minus y hat. So we decided that y, I said, okay, we didn't give that to you, but we should have. So we're going to say, if this was on a quiz, we'd give you a y value. Here we said y equals 1.0. So I'm going to plug that in. I'm going to plug that in here. And then y hat, we computed that earlier, and we got 0.91. There it is, 0.91. And then f prime of z3. Oh, yeah, we got to do a little bit of math. Okay, we're almost there. So f prime, and then z3 we did compute. So z3, we just got a value of 2.36, 2.36. So f prime of 2.36. So we're really almost there. Remember, we computed f prime back in number 6. We computed an equation for f prime. So let's go back to that real quick. I believe, yep, there it is. So cool. So let's just deal with this part for a second. So we have e to the minus z. This is what we computed in part 6, question 6. 1 plus e to the minus z squared, like that. So we can get out our calculator and plug in 2.36. So we have e to the minus 2.36, like that, divided by 1 plus e to the minus 2.36, like that, squared. I think that gets it. Let me know if you get something different. But I get, for this, I get 0.078 or 0.079. Okay, I think that's correct. It looks right to me. If you're doing this later and you find an error, just let us know. So I get this for f prime of 2.36. And now I'm really almost there. All I have to do is do minus times 0.79, 0.79, 0.79 times, so 1 minus 0.91 is 0.09 times 0.079. And we're really almost there now. All we should have to do is do the 0.079 term times 0.09 times, I'll just do one of these, 0.79, and I get 0.0056 is what I get. So the answer that I'm going to get is 0.0056. And if you find an error later, just let us know. It's easy to make errors when you're doing all this stuff, so make sure you double check on your quiz. But I get this. I get this for dJDW2, which would mean that if we're training a neural network, we should update our weights by basically taking a step in this direction. Oh, I think Ravina has found an error. Okay, interesting. Let's see if we can. It's 3:57. We have to hop on a call in a second, unfortunately. But let's see here. So Ravina, did I do it? Is it here? This should be 0.79. Is that right? Oh, I plugged it in wrong here. Oh, I see. For the last one. Ooh, we're super close, and let's see if we can get it. Oh, thank you, Ravina. Yes, I did. Yep, that is right. So this should be. I think I just need one more 0 then, right? So I think if I just add another 0 here, like I think we're in good shape. I think I'm just off by a factor of 10. Yeah, cool. Okay, thank you, Ravina. Awesome, good deal. It's always good to have people looking over your shoulder. Okay, so that oh, go ahead.
Sorry for the interruption. Actually, we just spoke with the group 4 people who has a 4 p.m. slot. We just confirmed that 4:15 slot works for them so that we can continue with the video.
Thank you, Arvin. That is very helpful. You're awesome. Thank you. It is nice to kind of get this knocked out. And how many folks have stuck around? Let's see. How are we doing? 39 folks are interested in this level of math right now. That's great. Or they're interested in their quiz grade, or they have some free time. All right, cool. Thank you, Arvin. That's awesome. So we'll push that. That's great at 4:15, so we've got a little bit of breathing room. I think we are just about done, which is great, but it's good to have that extra time anyway. So that is the answer to this question. And let me just kind of wrap up here, because now what we can really do with this little bit of extra time is I can just give you a couple tips for as you're looking at your quiz, as you're kind of reviewing this stuff on your own, where I'd like you to be. So again, the point here, I know this was a bunch of math. I promise this is the most math that we will do all semester. You won't see any more math than this. This is as deep as it goes. The point here is to really get you as deep as we can into how this stuff works, because we're going to be using the same exact math when we get to deep learning. It's going to be the same kind of thing. But here, there it's going to be kind of wrapped up in software for you. But if you really understand, I think, what's happening inside of this code, and what's happening inside of the code really is this math, it's going to give you better intuition for how these things work. So what we tried to do here today was to dive really, really deeply into how the math actually works, and to really kind of push your understanding of the calculus. And the quiz will cover some of that calculus. And I'll give you just a little summary of that now. So Hernan says, how will we know the hidden layer size? Yeah, so Hernan, that's a great question. So that's something that we're going to choose at the beginning. You might choose it when you're designing your neural network. When you're doing your programming challenge, I would experiment. Try different hidden layer sizes, because the hidden layer size will not be learned for you. You have to make that decision. So usually it's by experimentation. We went deep into deep learning. Yes, we did go deep, Sai. Yeah, hopefully it was helpful. So just the last thing I'll say is you're studying for your quiz. Please do review these notes. This is the best thing to look at. Also look at the Jupyter notebooks. But the backpropagation notes are the best thing to look at. We walked through the answers to, I believe, number 1 all the way through 11. There are 2 more pages of questions. These questions I will not quiz you on. If you want to look at them, please feel free. It mirrors the same stuff that's covered in the YouTube series. But really, if you understand number 1 through 11, you're going to be in good shape for the quiz. Walk through this on your own. What I really encourage you to do is to do an example like this. Maybe make up your own. If you really want to get gutsy, do it in Python and in code and in math, right? Then you really know if you have the right answer. You can do this in Python and do it in math, and make sure you get the same thing both ways. The last part of this is really just putting it back in Python. And that's what the second notebook does. So have a look at Neural Networks Part 2, the notebook, in GitHub. We won't have a chance to cover that before the quiz, so please have a little look at it. And I guess there's one concept that I do want to get across, so maybe we'll do a little discussion of that on Thursday if we have time. We'll figure something out. Because yeah, I might ask you a question like that on the quiz. There's probably about 10 more minutes of content that I think will be important. So I'm going to make a reminder today, and we'll make sure that you guys have a chance to think about that. Just to make sure you're prepared. But as far as math, going through 11, like this is it, right? So if you can get to here and you understand these steps, then you're going to be in great shape on the quiz, and you're going to have a better understanding of how neural networks work. So yeah, thanks for your time today, everyone. Thanks for bearing a little bit longer. I know it was a lot of content today, but this is like as deep as we go, all right? So this is as low as we're going to go into the deep math, how this stuff works, and from here on out, we're going to use more and more sophisticated tools. In about 2.5 weeks, you're going to be using PyTorch, which magically does basically all of this for you, which is pretty crazy. It's still worth knowing how it works, I promise. That's a good part of being in school, is you get to really dig into how stuff works. But PyTorch is going to do a bunch of this stuff for you, which is pretty cool. Okay, great. Well, thank you for your time today, guys. We will talk to you on Thursday. We've got a great guest lecture on Thursday. Please review David Deco's bio. He's going to be, I'm really excited for this guest lecture, so bring some questions. He is the man when it comes to manufacturing and computer vision. He has like 30 years experience, really cool guy, super nice too. Okay, guys, have a good week. We will talk to you on Thursday.